We have used an example in the last couple of videos dealing with voltage, where you have two plates that are positively and negatively charged. And that creates an electric field on the inside. So that's your electric field. And you have a voltage. They're separated by some distance, D. So we've used this example. In this video, we're going to talk a little bit more about it. A device that is set up just like this, that because of the separation of charge creating the electric field, is a device for storing energy. And such a device is called a capacitor. So we're going to talk about capacitance in this video. So a capacitor consists of two conductors that are close together but not quite touching. And because of that, you end up collecting charge on the surfaces, which builds up and stores electric charge, and thus you have potential energy. Now, capacitors come in all sorts of shapes and sizes, and let me explain it this way. Sometimes you have just air in between, sometimes you have an insulator in the middle, and sometimes the insulator is different. It varies from one thing to another. But the point being, there are lots of different types of capacitors that we can play with. So let's stick with the simplest form of a capacitor, and that's this parallel plate capacitor, which is connected to some voltage source, also known as a battery, which we'll talk about the battery in a bit. A battery is basically a glorified capacitor. Okay, so here's the setup. You have a battery which is connected by wires to the two plates. The positive terminal drives positive charges away and they collect on this plate. And the negative terminal drives negative charges away and they collect on the right-hand plate. Now, it's kind of cumbersome every time you want to draw a circuit to draw a battery, draw plates, and draw light bulbs and whatever else. So we use symbols. And that's what this figure over here in B is. Here's a symbol for a voltage source. It's just two parallel lines, one longer than the other. The longer line always indicates the positive terminal, the shorter line, your negative terminal. And then a capacitor would be the same thing, but the parallel lines are equal in length. And that's a capacitor there. So when we start doing circuit diagrams, you're going to see them looking this way. Now, the amount of charge that can build up on a capacitor is proportional to the voltage. So we get an equation that says Q is equal to some constant times V. And this constant C is called the capacitance of your capacitor. We measure capacitance in a unit of farads. If we were to solve for capacitance here, that would be charge divided by voltage. So the charge of 1 farad is going to be 1 coulomb divided by 1 volt. So that's another way to think of a farad is a coulomb per volt. By the way, the farad is named after Michael Faraday, who was the inventor of the generator. He will come up again later on. Very important figure in electricity and magnetism. So what does the capacitance depend on? It doesn't depend on voltage. You saw here that we solved capacitance equals charge divided by voltage. The capacitance doesn't depend on the voltage. The charge depends on the capacitance, but the capacitance and voltage are two completely different things. The capacitance does depend on the area of the size of the capacitor. I mean, if you have small plates here versus very large plates over here, the larger plates, that you can store a whole lot more energy on the larger plates than you can on smaller plates. So capacitance increases as the area increases. It also depends on the distance. If you have just a short distance here versus a large distance here, well, the farther apart they are, the less charge you're actually going to be able to build up. And so the smaller the distance, the more charge you can build up. So capacitance is inversely proportional to distance. And so with that, this is our equation for capacitance. This is epsilon naught. Remember that came up back in chapter 16. It's the value of 8.85 times 10 to the minus 12th coulomb squared per Newton meter squared. Also known as the permittivity of free space. So capacitance is this permittivity of free space times the area divided by the distance. Now that is a capacitor where there is air in between. In the next video, we're going to start talking about dielectrics, where you have capacitors that have some insulator in between the two plates.